Hello guys and welcome to another calculus video. In this video we're going to be tackling this insane integral right here. It's definitely one of the toughest integrals, if not the toughest integral that I've ever taken on, but something pretty interesting about it is that it actually, in this video, we're not going to use any special strategies to evaluate this integral. We're not going to use Feynman integration or the Laplace transform, infinite sums, or the Fourier transform, or master theorems, or anything like that. The only thing we're going to be using is clever substitutions and King's theorem. So if you're excited for the video, yeah, we're gonna. So yeah, let's jump right into the video. So first, let's show a quick result that we're going to be using in the video, which is the integral from 0 to pi over 2 of ln 1 minus cosine x. So first off, using King's property, this is equal to the integral from 0 to pi over 2 of ln 1 minus sine x, same integral. And the way we're going to solve this is we're going to let I equal the integral from 0 to pi over 2 of ln 1 minus cosine x dx. And we're going to let j be the integral from 0 to pi over 2 of ln 1 plus cosine x dx. So first let's calculate I plus j. And this is going to be the integral from 0 to pi over 2 of ln sine squared of x dx, which is the same thing as the integral from 0 to pi over 2 of 2 ln sine of x, right? And we know that this is just equal to negative pi ln 2. That's equal to I plus j. We're also going to calculate I minus j. So I minus j is the integral from 0 to pi over 2 of natural log 1 minus cosine x over 1 plus cosine x. Now we're going to go ahead and just divide by 2 on the top and bottom here. And we're going to use our double angle formula to convert this to the integral from 0 to pi over 2 of ln sine squared of x over 2 over cosine squared of x over 2 dx. Obviously, x over 2 is going to be u, and that means that du is going to be dx over 2. So we're just going to end up with 4 times the integral from 0 to pi over 2, because we brought this 2 out from this squared bit, of natural log of tangent x dx. Then we're going to let u equal tangent x, du equals secant squared x equals dx equals u squared plus 1 times dx. So let's fix that up. So we're going to have 4 times the integral from 0 to 1 of ln u over u squared plus 1 du. And if we just convert this into a power series, for 1 over u squared plus 1 equals sum from n equals 0 to infinity of negative 1 to the n, u to the 2n, and then go ahead and solve, you'll find that this is just equal to 4 times g, where g is Catalan's constant. So if we take I plus j plus I minus j, we're going to get 2i, right? Which is also equal to 4g, oh sorry, this is negative 4g, negative 4g minus pi ln 2. So overall, that's 2i, so that means I equals negative 2g minus pi over 2 ln 2. Right, let's go ahead and solve our integral. So the first step here is going to be to simplify the natural log a little bit. So we have integral from 0 to 1 of natural log square root x plus 1 over square root x plus 1 minus 1, all over square root 1 minus x squared dx. So the first thing we're going to do is we're going to multiply by the conjugate inside. So we're going to multiply by square root x plus 1 on the top and bottom. So we're going to end up with the integral from 0 to 1 natural log of square root x plus 1 squared over, and once we multiply all that out, we're just going to get x over square root 1 minus x squared dx. So if we split this natural log now, we're going to have 2 times the integral from 0 to 1 of ln square root x plus 1 over square root 1 minus x squared dx minus the integral from 0 to 1 of ln x over square root 1 minus x squared dx. This is a well-known integral. We just do x equals sine theta. So we get negative integral from 0 to pi over 2 of ln sine theta d theta, or pi over 2 ln 2. So our integral, which we'll call I equals 2 times the integral from 0 to 1 of ln square root x plus 1 over square root 1 minus x squared dx plus pi over 2 ln 2. Alright, I'm going to call this little integral right here I1. So solving for I1, we have the integral from 0 to 1 of ln square root x plus 1 all over square root 1 minus x squared. Now one of the key tricks here is to notice that square root 1 minus x squared is actually equal to square root 1 plus x times square root 1 minus x dx. And now the trick here is that we can just substitute u equals square root x plus 1, and then if we divide by 2 here and multiply by 2 here, du equals 1 over 2 square root x plus 1, which dx, which is just going to be this, right? So we can go ahead and make that substitution. So I1 equals 2 integral, okay, now we have to change our bounds. They're going to be going from 1 to square root 2. We're going to have ln u plus 1 over square root 1 minus x. But in this case, x is not our normal variable that we're going to want to be using. So if we go ahead and solve for x, we're going to find that it's just u squared minus 1. So we're subtracting u squared minus 1, so we're going to end up with 2 minus u squared du. Now, in order to get rid of the 2 minus u squared on the bottom, we're going to want to substitute square root 2 sine theta equals u. And that means square root 2 cosine theta d theta equals du. And this is actually equal to square root 2 cosine theta d theta because of how trigonometric substitution works. So we're going to make our substitution here. I1 equals 2. And now we're integrating from 1 to square root 2, but now we're making our substitution. So square root 2 sine theta equals 1, which means that sine theta equals 1 over square root 2. So we're going from pi over 4 to square root 2, which is just going to be pi over 2. And now this bottom part is absorbed by our differential, right? So we're just going to have natural log square root 2 sine theta. Oh, that's not 2 sine theta plus 1. Now, here comes the amazing trick right here. So some of you may know this very, very, very useful identity, which doesn't show up very often, but when it does, it can absolutely destroy lots of cool looking integrals. Square root 2 times sine of x plus pi over 4 equals sine x plus cosine x. So this looks a lot like what we have here because we have square root 2 multiplied by sine of x. So in order to simplify this, all we're going to have to do is just replace theta with some x plus pi over 4. So I'm going to do exactly that. I'm going to let theta equal x plus pi over 4. So we're going to get I1 equals 2 times the integral from, now we're going, d theta of course equals dx, so we don't have to worry about that. We're going to be integrating now from 0 to pi over 4. And we're going to get natural log, and now we have square root 2 sine x plus pi over 4, so that's just going to be sine x plus cosine x plus 1 dx. And another thing that we can do here is if we substitute u equals pi over 2 minus x, then we find that I1 also equals 2 integral from from pi over 4 to pi over 2 of natural log sine x plus cosine x plus 1 dx. So if we go ahead and add these two together, we get 2I1 equals 2 integral from 0 to pi over 2. So now we're integrating all the way to pi over 2, which is much more easy to deal with. And we can go ahead and cancel these 2's. So this is now the integral we're trying to solve. It's a nice trigonometric log integral, so let's go ahead and solve it. So we have I1 equals integral from 0 to pi over 2 ln sine x plus cosine x plus 1. Alright, now this is a bit of an interesting integral that we're dealing with here, and there's a few different ways that we can take this on, but really the genius trick that comes here is, although this is not very easy to deal with, there's no good way to factor it, there is a way to make it factorable. And what we're going to do is we're going to square the inside here, and we're going to divide by 1/2 on the outside. Now, just something useful to remember is that x plus y plus z squared equals x squared plus y squared plus z squared. Just kidding, you also need plus 2xy plus 2yz plus 2xz. So we're going to have 1/2 times the integral from 0 to pi over 2 of natural log of sine squared of x plus cosine squared of x plus 1 plus 2 sine x cosine x plus 2 sine x plus 2 cosine x. And now once we simplify this, we see that this is just equal to 2, right? So we have a 2 in all of these terms, so we can just go ahead and bring that 2 outside. So we're going to bring out ln 2 from all of this, right? And we're going to get pi over 4 ln 2, right? Plus integral from 0 to pi over 2 of natural log of 1 plus sine x plus cosine x plus sine x cosine x. And some of you may have seen the magic that happens right here, that this just factors to 1 plus sine x. And so now we have pi over 4 ln 2. This is still a 1/2 in here. And note that we're going to now have plus 1/2 integral from 0 to pi over 2 natural log of 1 plus cosine x plus natural log of 1 plus sine x. And notice that both of these integrals are the same as we showed before because of King's property. So overall, our answer is just going to be, since we're multiplying by 1/2, that's going to cancel with them. We're going to have negative pi over 2 ln 2 plus 2g, as we said before. I'm sorry, I just realized that at the beginning we had I plus j equals negative pi ln 2, and I minus j equals negative 4g, and then I actually ended up solving for I, but we needed to solve for j. So if we go ahead and solve for j right here, we can see that it's just going to be negative pi over 2 ln 2 plus 4g. So that's why we got this answer right here, or plus 2g, not plus 4g. Plus 2g, so that's what we have exactly right here. And you can see that these are going to sort of cancel, so we're going to have negative pi over 4 ln 2 plus 2g. And that's our result for I1. If we go ahead and remember what our answer was, we said that I equals 2I1 plus pi over 2 ln 2. So we can see that this is just going to cancel with that, and we're just going to end up with I equals 4G, just like the cellular internet, right? So that is our answer to this beautiful, beautiful integral, something that I spent a lot of time on because this was a really tough integral. I hope you guys really enjoyed the video because I had a lot of fun with it, and this was definitely one of my favorite integrals that I've solved. So yeah, Hope you guys enjoyed the video, and I will see you next time.